Hi there, folks. This is the Unit 7 review, and as always, I'm amazing Mr. Jansen. So away we go. If we look at these first couple, they're just asking us to evaluate. So in other words, we're just simplifying using rules of exponents and then just kind of multiplying these things out, that kind of stuff. So like right here, a negative exponent means I flip this thing. So this is 1 over 4 to the second power. And then I just raise these to their respective powers. So that's 1 over 16. Here, 2 to the 4th power is 16, and that's 16 over 1. Now when I multiply these, 16 over 16, which equals a 1, and that's it. Okay, so we're just simplifying it. Our calculators can help out with us, but we don't want to express that first one as a decimal. We want to keep it as a fraction, so we can simplify this a little bit easier. Okay. The next one, anything to the 0 power, except for 0, of course, but anything else to the 0 power is 1. So that's the answer for this one. All right. This guy, when we have a fraction raised to a power, I just raise each of them individually. So 2 to the 3rd power, that gives us an 8. And now 3 to the 3rd power is a 27. And that's it. That's all there is to it. Okay. This one, we got to follow order of operations. So we have to do the exponents first. So here, when I raise it to a power, I multiply the exponents. So that's going to be 8 to the 10th power. And notice I'm leaving it this way for now because I want to simplify this as far as I can before I actually get on with the math on that. Here, when I raise this to a power and multiply the exponents, that's 8 to the negative 12th. And now, when I multiply, I can add the exponents, so that's 8 to the negative 2nd. And you see what that's done is it makes this a lot easier because now I flip this guy. Well, 8 to the 2nd power is 64. And had I started plugging those things in right away, I'd have some really ridiculous numbers when I start doing things like 8 to the 10th. But when it's all said and done, I only end up having to do an 8 to the 2nd. That's where the power of exponents, the power for the rules of exponents comes in. Same thing here. If I multiply these, when I multiply, I add the exponents. That's going to be 5 to the 3rd power. And that's a lot more manageable than doing things like 5 to the 11th power. So that's 125. This one, remember the negative exponent flips this thing, so it's going to be a 4 over 1 raised to the 4th power. So really it's just 4 to the 4th power. And 4 to the 4th power is 256. Okay? And then these guys getting into our rules of exponents a little bit more when we're talking about variables and that kind of stuff. So here, the first rule of exponents I see I can use is right here, this whole thing in parentheses raised to the 0 power, that's a 1. Now I have 5 times 1 times e to the negative 3rd. 5 times 1 is just a 5. Then remember negative exponents, we send that guy to the other side of the fraction bar, and we make it positive. Okay? Here when I multiply, remember the rule is when I multiply, I add the exponents. So here I add the exponents, just y to the 13th. Okay? This one I'm multiplying, so I treat numbers the same way I've always treated numbers. Negative 4 times 7 has always been a negative 28. It will always be a negative 28. And so in this scenario, it's a negative 28. Okay? But when I multiply the exponent, when I multiply the variables, I add the exponents. Okay? So that's rules of exponents. I add those. So that's a to the 11th power. Okay? The next one, again, following order of operations, I do the exponent first. So like here, there's not really much I can do at the moment. But this guy raised it all to the second power, and this is the one that students typically have an issue with. Like if you were to ignore that variable, if I only had the negative 3 here and I ignored the h, it would just say negative 3 in parentheses to the second power, which is a 9. Okay, so that's the way I treat that. But then rules of exponents, I multiply the exponents, so that's h to the negative 8. Okay, so again, think about numbers the way that we've always thought about numbers, and then separately take care of those rules of exponents. And now I'm multiplying. Negative 2 times 9 is a negative 18. And I add the exponents. That's h to the negative first. And now again, take care of negative exponents. So the negative 18 stays where it is because that's a negative 18, not a negative exponent. The only negative exponent switch to the other side. Okay? And you can write the little 1 in there if you really want to. You don't need it though. Okay? This one, when I raise it to a power, I multiply the exponents. So that's going to be a g to the 48. This one, following rules of exponents, when I raise it to a power, I multiply the exponents. So that's a negative 18. And again, I'm just doing the exponents because that's what comes first in order of operations. Here I multiply the exponents. That's a y to the 15th. And now when I multiply, I add the exponents. That's y to the negative 3rd. And now, of course, I take care of negative exponents. I flip that guy, so it becomes 1 over y to the positive 3rd. Okay? So again, I always follow order of operations, do my rules of exponents as I go, and then take care of negative exponents. This one, same kind of thing. When I divide these things, I subtract the exponents, so that's x to the 12th. Here, same thing. 27 divided by 3 is a 9, but now rules of exponents, I subtract the exponents. That's n to the ninth. This one, I would follow rules of or follow order of operations inside the parentheses. There's nothing I can do inside the parentheses. I can't divide any of those things nicely. So now I move on to the exponents on the outside. 4 to the third power is a 64. And now I multiply the exponents. That's b to the 15th. Same thing with the denominator. 3 to the third power is 27. And now I multiply the exponents. That's a to the sixth power. These guys looking for the missing value here. Here it's multiplication, so I would be adding the exponents. So in other words, what plus a negative 3 equals a 6? And the answer there is a 9. 9 plus a negative 3 equals a 6. This one, when you notice this thing, I have an n to the 21st in the denominator, which means I would have to get a negative exponent in order to send it to the denominator. So I basically have to ask myself, when I raise it to a power, the rule is multiplication. So 3 times what will give me a negative 21, because that's how I would end up with a value in the denominator. And the answer here is, of course, a negative 7. This one, rules of exponents, I would multiply. So, or when I'm multiplying, I add the exponents. So that would give me a d to the third if I simplify a little bit. And then there's my blank that I'm still looking for. So again, rules of exponents, when I multiply, I'm adding the exponents. So 3 plus what will equal an 11? Well, that's an 8. Okay. Now we get into some of these more complicated ones. Again, follow order of operations. Do one operation at a time. So you're doing one rule of exponents at a time. So order of operations, I start inside the parentheses. So inside the parentheses, I do the division first. 14 divided by 7 is a 2. But now my rules of exponents for division, I would subtract the exponents. Just be really careful here with the signs. Negative 5 minus a negative 2. And if you need to take it off to the side, negative 5 minus a negative 2. See, that's adding the opposite. That's an x to the negative third now. Okay? Here, when I divide and subtract the exponents, that's y to the sixth. And now I just take a pause, I take a deep breath, and I think about the next thing that I'm doing. The next thing I'm doing is raising this to the fifth power. Well, 2 to the fifth power, that's same old, that's 32. But now I have to think, when I raise it to a power, what do I do with the exponents? I multiply the exponents. So it's x to the negative 15th, y to the 30th. And now I'm going to take care of any negative exponents. The only thing here that has a negative exponent is that x value. So the 32 stays where it is. The y to the 30th stays where it is. But the x to the 15th goes in the denominator. Okay, that's how I take care of negative exponents. I flip it to the other side and make it positive. Here, order of operations, I would do the exponents first. So 3 to the second power is a 9. And I multiply the exponents, that's x to the 8th. Okay? Same thing here. 9 to the negative second power. So again, take it off to the side if you need to. 9 to the negative second power. That's 1 over 9 to the second power. And 9 to the second power is 81. So this is 1 over 81. And then I multiply the exponents. That's x to the negative sixth. Now I'm multiplying, so I take a deep breath. I think, okay, multiplication. 9 times 1 over 81 is the 9 over 81. I'll reduce that later. And then when I'm multiplying, I add the exponents. That's x to the second. Okay? If I combine this back into one fraction, it's 9x to the second over 81. But now reduce the fraction. 9 over 81 reduces to a 1 over 9. So it's just going to reduce to this. Okay? So again, we deal with numbers the same way we've always dealt with numbers, and then use our rules of exponents for the variables. This one, same kind of thing. If I have negative 2 in parentheses to the fourth power, that's a 16. When I raise it to a power, I multiply the exponents. That's y to the negative 16th. And this guy just tags along for the ride for now. And now I'm multiplying. 5 times 16 is an 80. When I multiply, I add the exponents, so that's y to the negative 10th. And now the last thing I like to do is take care of negative exponents. So I'm going to send that guy to the denominator. Now it's a positive 10 for its exponent. Okay? This one, here's the one scenario in which it's usually better to take care of negative exponents first. Okay? Normally I would follow order of operations. I'd start inside the parentheses. But when I have an entire fraction raised to a negative exponent, it's a lot easier just to flip that whole fraction. So if I flip that whole fraction, so this is now going to be my numerator. This is now going to be my denominator. And again, normally I always deal with negative exponents last, but in this scenario, it's a lot easier, especially for students, to flip this guy, and now it's a positive 2. See? Using that negative exponent, I flip the whole fraction. Now let's start inside the parentheses. Inside the parentheses, I have 5 over 3. When I subtract the exponents, that's x to the negative 10th. Here, when I subtract the exponents, that's y to the 5th. And now it's all raised to the second power. I'll just raise each of these to the second power. Like 5 to the second power is 25. 3 to the second power is a 9. When I raise things to a power, I multiply the exponents. That's x to the negative 20th, y to the 10th. And now let's take care of the remaining negative exponents. Since I already have a fraction established with a 25 and a 9, I just say, okay, that x to the negative 20th, negative, I flip it to the denominator. So the x to the 20th goes down here, and the y to the 10th stays in the numerator. Okay? Use the fractions already given to as your numerator and denominator, just start moving things. Okay? This one, again, order of operations, I would start in that numerator with the exponent. So 3 to the 4th power is an 81. And now I multiply the exponents. And be careful here. Remember, when you don't see an exponent written, it's a 1. So that's x to the 1st right there. So just be aware of that. So now when I multiply that, that's going to be an x to the 4th and a y to the 8th. Okay, that's my rule for exponents there. And now I'm going to multiply in the numerator. Again, when I multiply, I add the exponents. So here, that's a 162. I add the exponents. That's x to the 8th, y to the 13th. Let's see, x to the 7th, y to the negative 3rd. Okay. And now from here, I subtract the exponents. And, I'm doing the division. When I'm dividing these things, these don't divide evenly, but I still need to reduce the fraction because that's what I would always do with numbers, okay? So the 162 over the 8, I can divide each of those by 2, so that's going to be an 81 over 4. Okay, so still reduce those fractions. And now I subtract the exponents. Actually, let me kind of split this up. I'll subtract the exponents, that's x to the 1st, and then y to the 16th. And now I can combine it back. I could leave it like this, that would be fine. But I like to write it as one big happy fraction. That's it. Okay. But look at this one. Midichlorian is approximately 10 to the negative 7th grams. About how many midichlorians are in a 100 gram vial. So when you look at something like this, if it's 100 grams, and we know that each midichlorian is the 10 to the negative 7th grams, essentially what I'm doing is I'm doing 100 divided by this guy, okay? And it's just like if I said, there's 25 cents in each dollar, and I have $100. How many quarters do I have? You would take the 100 and divide it by 0.25 to figure out how many quarters it was. It's the same thing here. You're dividing this, and there's a couple ways you can approach this. We could kind of just use our calculator, and it'll kind of spit out an answer for us. But if we wanted to think of this is like 10 to the second power. We wanted to use our rules of exponents. And now when I divide these, I subtract the exponents. So that's 10 to the 9th power. And then if I wanted to write this out, it would maybe make sense to just say, 10 to the 10th power. Sorry, 9th power, I said 10th, but 9th power would be this. Okay, so it looks like 1 billion. And that's it. The next one, going the other way, how many grams of midichlorians would 1 million midichlorians yield? So again, this is the number of midichlorians. I'm just going to multiply that by 10 to the negative 7th power to figure out how many grams it is. And again, I could just use my calculator to kind of help me out on this, but I could also think of that 1 million as 10 to the 6th power. Sorry, I got a little tickle in my throat. And now when I multiply, I add the exponents. So it looks like that's going to give me 0.1. Oh, sorry, 0.1 grams. If we take a look at these next couple, it says state whether each equation represents an exponential function. If it does, determine if it's growth or decay. So for this one, remember exponential functions are of the form y equals a times b to the x. So we're just looking to see if it's in that format. So if we look at the first one, that's in that format. However, that negative exponent doesn't quite match that format. If we took care of that negative exponent, it would actually be 1/5 raised to the x power. And so, yeah, this one's exponential, but now we can see that it's exponential decay because the b value is that proper fraction. So the answer here, yes, this one is, but it's decay. Okay, this one doesn't quite look like we normally would have it, because normally we'd have the parentheses, but it's still y equals a times b to the x. So this is my a value, this is my b value, and this is my x. Normally we'd see it written like this instead, but it's the same thing. So this one, yeah, it's in that format. And this one's growth because the b value is bigger than 1. Okay? This one does not fit the mold because this is slope-intercept form. This one's actually linear. So no, that one's not exponential. And then this one, it's in that format, y equals a times b to the x. There's nothing we have to do to change it to make it look more like that format. This one's set up perfectly. So this one's yes. And this one's actually growth because the b value, again, is greater than 1. Don't be fooled by the fact that it's a fraction. It would have to be a proper fraction in order for it to be decay. All right? These guys determine if it's an exponential function and whether that's growth or decay, and then write the equation. So remember, the pattern we're looking for an exponential function is if we're multiplying by the same thing each time. So like this one, looks like we're multiplying by 2 to get from one term to the next. So because we're multiplying each time by the same thing, this one is exponential. So the equation, remember, a is the y-intercept, b is the thing we're multiplying by. So that's my equation. Now I can tell that this one is growth. Okay, that one is an exponential function. This one, it looks like we're dividing by 3 each time, which really means we're multiplying by 1/3. And so that makes this an exponential function because we're multiplying the same thing each time. A is the y-intercept, b is the thing we're multiplying by. So now I can see this as an exponential function, but it's decay this time because b is between 0 and 1. This one, it looks like divided by 4 times 1/4 is the pattern for each of these. And then from there, we can write the equation. It's y equals. This one, we can't quite see the a value. The y-intercept, I'd kind of have to extend the pattern here. So if I kind of extended the pattern back to 0, well, this would be times 4, and I'd end up at a 256. Okay? So then what happens here is the 256 is my a value, and this is 1/4 raised to the x. So this one's decay. This one's a little bit trickier than the rest of them. And as we start to look at this thing, it's probably hard to identify what we're multiplying by. Remember, the trick, though, is just take one of the terms and divide by the term before it. If I take 3 divided by 2, it gives me 3/2, and then check it. So 2 times 3/2 does give me a 3, and then 3 times 3/2 does give me the 9/2, and then times 3/2 does give me the 27. Sorry, that's supposed to be a 4. That was a typo. So this one doesn't quite work out when I get to that last one, but pretend that I didn't make a typo and that was a 4 there. And so if that's the case, again, if you work backwards here, and again, that's a little bit trickier for this one, we would have to divide by 3/2, which is multiplying by 2/3. So if I worked my way backwards to 0, it would be a 4/3 for that guy. And you can use your calculator to help you out with that. So y equals 4/3 and then 3/2 raised to the x. And this one is growth because the b value is bigger than 1. Okay? All right, for these guys, it says to graph. And once again, remember the a value is like our y-intercept. So like right here, that's the y-intercept is the 2. And remember the b is what we're multiplying by, okay? So this is what we multiply by. So in this one, we've got a y-intercept of 2, which is right here. And then we're multiplying by 3 each time. So I just start with a 2 and say, okay, 2 times 3 is a 6. That's my next y value. And then 6 times 3 is an 18. That's my next y value. 6. Oh, it's going to be way up here somewhere. Going the other way, we just reverse that process and say, okay, divided by 3. So 2 divided by 3 is a 2/3. And then divide that by 3, and then divide that by 3. And again, we're just estimating we get closer and closer to this line without actually touching it. That was terrible. I missed by a mile on that. Let me try again. There we go. And that's it. That's exponential growth. If I look at the next one, it's got a y-intercept of 5. And then I'm multiplying by 0.2 each time. And so you just take 5 times 0.2, which gives you a 1. And do that times 0.2, and then times 0.2, and then times 0.2. And again, once we get to a certain point, we're just estimating. Going the other way, it's like divided by 0.2, which is like times 5. So that's going to give me a 25 going the other way, which again, it's going to be way off the graph. So this is a very steep kind of curve. Okay. And again, I'm just estimating that last one because again, it's way off the graph. Okay. This one, same kind of thing. It starts at a 4. And then I'm multiplying by 5 over 4. And if you want to rewrite that, that's 1.2, 1.25. If you want to write that as a decimal, that's fine because that's essentially what you're going to be using to plug into your calculator anyway. So then if you do 4 times the 1.25, that gives you a 5. And then again times the 1.25, that gives you a 6.5, or sorry, 6.25. And then times the 1.25. And again, just use your calculator for this. That gives you a 7.8125. And you just keep multiplying by 1.25. That's going to be a, let's see, 9.765. Let's see, 12.2-ish. And that's probably good in that direction. Going in the other direction, just reverse the pattern. If going one way was multiplying by 1.25, going the other way is dividing by 1.25. So if you divide a 4 by 1.25, it gives you a 3.2, right about here. And then again, divide by 1.25, and just keep going and plugging these in. 2.56 divided by 1.25 gives you a 2.048. Essentially a 2, divided by 1.25, 1.6-ish, divided by 1.25, and just keep going, plot as many of these as you can, make a nice, neat, accurate graph. Oh man, right around 1. Okay, wow, I might as well do the last one. I was going to quit there, but and so we get this nice, gradual looking curve here. Okay, and that's it. So again, A is the y-intercept, B is what you're multiplying by each time. Okay. This one, a population of amoebas in a Petri dish will double in size every 30 minutes. The initial observed population is 600. And so again, this is being described in terms of multiplications doubling in size. So that means we're going to write it in that format of y equals a times b to the x. So y equals a. A is the initial amount, so what we start with, the 600. B is what we're multiplying by, which is the 2 this time. And then from here, you could just say x if you want, where x is like the number of doubles, the number of doubling periods. Or if you want to use a better version of this thing, again, it doesn't matter as long as you plug the right thing in for that exponent. So here I would say times 2. But that numerator, it doubles every 30 minutes, which means each hour it doubles twice. So if I call this 2x, well, now x equals the number of hours, which is just a little bit easier in terms of plugging things in. Okay? If you look at the first one, 4 hours, well, that's how many 30-minute increments? That's 8 30-minute increments. So you just have to think a little bit more as you go to plug this thing in. So here you'd plug an 8 in because that's how many doubling periods it is. But here, even though it's a little bit more work to set up the equation, actually using it is easier because I just plug the number of hours in. I plug the 4 in. Okay? Still gives me the same thing. It gives me an 8 for that exponent. So now, again, I just plug it into my calculator. When you do it on the calculator, remember, you just make sure you do the exponent first. So you do 2 to the 8th power, which is the 256, and then times that 600. So it looks like it gives you 153,600. And you get the same thing over here as well. Okay? But again, it's being described as soon as you see it saying, it's doubling or tripling or times this or times that. It's being described as y equals a times b to the x. So that's the way you write your formula. Something like this guy, family purchases a house for 175,000. Each year the value of the house increases by 2.5%. Find the value of the house after 10 years. Well, this is being described as a percent increase, which the giveaway there is that y equals a times 1 plus r raised to the t. Okay? And again, you don't have to memorize that formula. I'll give you that on the test. So here I go y equals, the initial amount is 175,000. 1 plus the rate. Remember, whenever you plug a rate in, you have to do it as a decimal. So 2.5%, remember, 2.5% means out of 100. So that's going to be 0.025. Okay, so 0.025 here. And then raised to the 10th power. And just make sure your units match. It says each year it's 2.5%, and the time is in years, so we're good to go on that. And you can simplify a little bit before you plug it into your calculator if you'd like to. You don't have to. You can plug it right in like this, but it's just a lot to plug in if you do it like that. If you just do that one little piece of simplification. Oh, almost plugged it in my calculator wrong. So you do that 1.025 raised to the 10th power, and then multiply that by the 175,000. And because we're talking about money here, you should automatically round to 2 decimal places. And this is 795, so that 9 rounds up to a 10, making this an 80 cents for that guy. Okay, but again, if it's money, always round to 2 decimals. All right. This one, a car costs 35,000 when it's brand new. Each year it depreciates 18%. Find the value of the car after 7 years. Again, because we're talking about a percent decrease this time, we know it's that formula y equals a times 1 minus r raised to the t for our exponential decay. And we just plug away. See, that's the 35,000. 1 minus. Again, once again, the rate we plug in is a decimal. That's 0.18. Raised to the 7th power. And this one, some of you might need to use your calculator to simplify this guy and get the 0.82. Okay? Don't make a silly mistake trying to do too much in your head if you need a little help with that. $1 minus 18 cents. How much cents do you have? Think of it that way if you need to. But now I plug it into my calculator, the 0.82 raised to the, 7th power. And then times that 35,000. Prepare to be disappointed. Your car's only worth $8,724.99. Appreciation's a bugger. All right, last, I think this is the last one. Yeah, last one here. For this one, again, there's two options here. There's two formulas I gave you. Again, we're talking about a percent increase, so you use that y equals a times 1 plus r raised to the t. Okay, because that's a growth formula. Or we could use the modified version that's locked into year, because this is APR, which is annual percentage rate. And that's this one. It's the y equals a times 1 plus r over n raised to the nt. And again, I'll give you both of these formulas. The second one, you just have to know what n really represents. The first one, we just have to be very careful, very cautious to make sure our units match. So right now, this is APR compounded monthly. Those don't match. It's 3% per year compounded per month. Okay, so if it's compounded per month, I need a percentage that represents months. So it's 3% each year. Well, each month then, well, divide by 12. And now this will tell me what it is monthly if I divide by 12. So that's 0.25. And again, that's 0.25%, which is a per month. But keep in mind, we'll plug that in as a decimal then, so that'll look even more different. And then 35 years, well, I just converted the percent to months, and it's compounded monthly, so the time should be in months. So I'm going to take that 35 times the 12 to figure out how many months that is. Oh, it's like 420. Again, that's months. But now when I plug this in, all the units are going to match. And again, that 0.25% is a decimal, is 0.0025 raised to the 420. Okay, per month, compounded monthly, times in months. And now just calculator work. That's going to end up being a 1.0025 in there, raised to the 420th power, and then times that 25,000. So it looks like I end up with 71,347 dollars and 73 cents. It's not a bad chunk of change. Okay. The other version of this thing, same thing, but even though it looks more complicated, it ends up being a lot easier because everything's accounted for us. I don't have to think that much. I just got to plug in. So initial amount, right here, the rate, 3% is 0.03. Up here, the time is 35. See, this thing's locked into years. We just have to remember that n is how many times a year it's compounded. So it's the yearly compound. So like if it's compounded quarterly, we'd plug a 4 in for n. If it's compounded biannually, we'd plug a 2 in for n. Well, this one's compounded monthly. I'll plug a 12 in for n. Okay, 12 times a year. And now I just simplify it. It's using my calculator to just simplify this thing. And yeah, I could punch it into my calculator exactly the way it's written, but it can be a little dicey to do that. So I would probably start with this 0.03 divided by 12, and that'll give you the 0.0025, which should look pretty familiar. And then the 12 times 35 gives you the 420, which should look pretty familiar. Now I'm back to where I was with the other example. I finished this thing off by plugging it into my calculator, and I get the same thing. Okay, so again, either formula works, but I think that first one is just a lot more thought involved. The second one takes all the guesswork out of it. You just have to know what n represents. Okay, hope this was helpful, and good luck on your test.